Also, it's because some factor that many international conference also call for paper and have the deadline similar to this conference. And we trying not only the acceptance rate increase acceptance rate, but also the number of submissions. Especially, we are trying to call our colleagues from other countries like Taiwan, Korea, Philippines, Thailand, to submit their paper to our conference. Lastly, we would like to thank the organizer, the strongly support from the UIT, from Vietnamese section in publish our paper on IEEE Explorer. We thank Vietnamese Association for Patent Recognition for technical support and sponsor to our conference. We thank all the authors, reviewers, and especially our keynote speakers. We have 4 keynote speakers this year: Professor Chinh Chung Huang from National Chung Cheng University of Taiwan, Professor Minh Hoai from State University of New York, USA, Professor Chuan Chen. Tomorrow we have his keynote speaker from Deakin University, Australia, Professor John Hodder from University of Utah University this afternoon. We thank all participants and UIT staff and volunteers for their contributions to this conference. And thank you very much and wish you all a successful conference and enjoy your stay in Ho Chi Minh City. Thank you.
Okay, let's go to the first session. Good morning. So my name is Duy Đình Lê. I'm very happy to be a chair of this sessions. Okay, let me introduce Professor Minh Hoài Nguyễn. So Professor Minh Hoài Nguyễn is an assistant professor of computer science at Stony Brook University. Prior to Stony Brook University, he was a research fellow at Oxford University, working with Professor Andrew Zisman. He received a Bachelor of Software Engineering from the University of New South Wales in 2006 and a PhD in robotics from Carnegie Mellon University in 2012. His research interests are in computer vision and machine learning. In 2012, Nguyen and his co-author received the Best Student Paper Award at the IEEE Conference on Computer Vision and Pattern Recognition. So today his talk is Attentive Human Action Recognition. So we are looking forward to his talk. Thank you.
Thank you very much, and good morning, everyone. It's my honor to be here and to give the first talk. So I'm going to talk about human action recognition, but before I talk about the technical part, let me tell you a little bit about what my research, my research interests are. Okay, so I'm interested in human behavior analysis, and for some reason, all the title has been it doesn't in a way. Okay, so yeah, I think it's important for you to see the title of the slide. So I'd like to maybe take a couple of minutes to try to. Okay, what should we do? Scale. Is it better? Oh, same thing. I think it's going to be the same. What should I do? I think let's see if we can resolve the problem in 2 minutes. If not, then I just continue. But I hope. Can we remove this curtain a little? Well. How do I try? No. All right. Okay. So, all right. So no problem. I want the slide for speak for themselves, but they cannot, so I speak for them. Okay. So, okay. So, my main interest is human behavior analysis, and so one of my research direction is. Oh, do you see it? Oh, okay. So they try to, given a video, we want to develop algorithm to recognize action, interaction, and activity of people in the video. Also, by human behavior, I mean facial behavior. Given a video of a person, we want to analyze this and understand how happy or how depressed a person is. By human behavior, I also mean gaze and visual attention. If I show a viewer an image or a video of a person, we want to predict visual attention, where a person is going to focus their attention on if you show them an image or a video. So by human behavior, by analysis, I mean to develop algorithm for recognition and prediction. Recognition refer to, basically analyze a pre-recorded video and understand recognize the category of the action. Prediction means you try to predict what's going to occur in the future based on partial observation. But prediction in general is very difficult. So there's, the third category that I'm interested in is, I call it early recognition, recognizing ongoing activity. So an activity has already started, but it hasn't finished yet. And we want to recognize this activity as early as possible. Okay, so why should we care about human behavior analysis? Well, there are many applications of human behavior analysis. For example, in security, once a bad event happened, we can try to go back and analyze the activity of the people in the crowd and to figure out the people responsible for the event. Right? Human behavior analysis can be very useful for healthcare. In the US, there's like 3.4% of people suffer from major depression. So if we have a more subjective method to evaluate and diagnose depression, then we can improve the quality of healthcare. Human behavior analysis is also important for human-robot interaction. Suppose that you want to build a robot that can fluently interacting with a human, then the robot must be able to kind of anticipate the behavior of the person. The final kind of example for an application of human behavior analysis is in network optimization. Here, so here in this case, if we want to save the bandwidth of the network, and if we know that a person is more likely to look at some certain area of an image or video, then we don't have to perform like high definition streaming for as the entire part of the video. Nowadays, we see more and more of like 360 videos, and for 360 videos, if you know, performing high definition streaming for the entire video is still very, take a lot of bandwidth, so this could be very useful. Okay, so my main problem that I'm interested in recognition, early recognition and prediction of human action, face behavior, and visual attention. I'm also working on supporting problems. For example, for human, in order for us to recognize and predict human behavior, we need to know where they are and also detect the body parts of the people. So I'm also working on human and body part detection, and by body part I mean like hands specifically. I'm also interested in visual counting people in a crowd or counting similar objects in images. So in human behavior analysis, the problem is usually very difficult. And one of the problems is we don't have a lot of annotated training data, and sometimes the data we have is weakly or noisily labeled data. So one of my interests is to address the fundamental machine learning problem underlying this computer vision application. So I developed algorithm for for machine learning algorithm for unlabeled sample, weak and noisy annotated samples, or how to learn from complementary samples. A lot of these questions, if you want to analyze and recognize and predict human behavior, we really need to kind of understanding fundamental question in human behavior, perception, and learning. And I collaborate with people in psychiatry and psychology to address this problem. So for today, I'm just going to focus on one particular problem. I will talk about recognition of human action for using complementary samples. So this talk is based on two papers. One is okay. All right, I don't know what happened. Okay. All right. So this talk is based on two pieces of work. One on CVPF 18 on pulling action out of context, and the second one is under review, and but it's already on archive, and you can take a look at it if you are interested in. Okay. And So this is a joint work with my students, Zhang Wang and Ving Chen, and also the Facebook team, Lorenzo Torresani and Gida Bertasios. Okay, so so I'm interested in recognizing human action in video, and the type of actions that we are looking at right now is like, say, for example, run, drive, or kiss in the video. So human action recognition is very challenging due to, first, the subtlety of the human action in the video, and second, the complexity of the video space. So it is very difficult to identify and attend to the relevant information. Now, a common approach for human action recognition would be the following. We should collect positive and negative data and train a classifier to separate between the positive and negative examples. For example, consider training a KISS classifier. What we do is we are going to collect positive examples of a KISS, right? And we consider negative examples as video clips of other type of human action. And once you have these two sets of training data, you can train your favorite classifier, such as an SVM. Okay? But the problem with this approach is, in the positive example, not only we have the KISS action, but also have the context. So essentially, what the classifier learns is not the actual content of the action, but something like for both the action and the context. What the context? So in this case, for example, like in a lot of KISS video, you see that the camera, moving very slowly, starts zooming in or panning around the two people kissing. So what the classifier is actually learning is the motion of the camera, not the actual content of the kiss. Okay? So, so there are various types of contexts here. So for example, background context like a kiss is more likely to occur in a living room. It could be camera context like slow panning camera, slow music. And it could be situation context, like a kiss is more likely to occur after a dance, right? Now, context often co-occurs with the action, so the learn classifier focuses on the contextual cues instead of the action content. So, context is very useful for recognizing the action, but at the same time, if you want the classifier to generalize well beyond this, to different situations, then it's not going to work well if the context is different. For example, if you want to train a classifier to recognize, say, toothbrushing, and it's brushing teeth usually occur inside a bathroom. So if the classifier doesn't see the bathroom, then it won't be able to recognize the brushing teeth action, okay? So our goal in this work is to train a classifier that explicitly separate between the action and the context. But the technical challenge that we have is the context is always co-occur with the action. So to some extent, if you just have two sets of training examples, positive and negative examples, then it's impossible to separate between the action and the context. All right. So one approach is to provide detailed annotation for the training examples that we have. For example, given if you want to annotate a handshake, what we want is, say, a detailed annotation in a spatial temporal location of the handshake, and then someone going to indicate where this handshake is, and also what part of the video correspond to the context. Now, but this approach is, but it's very difficult to obtain detailed annotation. First of all, this is a laborious process, and it's unscalable. Imagine that you have to do it for every single example, and for every action, like you have thousands of examples for each action category, and if you have 1,000 categories, then how much time it takes to label this data set. But more problematic, something more problematic is it actually very ambiguous. For example, if I just ask two people to annotate the temporal location of a handshake, when would you consider the beginning of a handshake? When the two people, when the two hands are in contact, or when one person starts extending the hand toward the other, the second person. So multiple people going to give very inconsistent answer for the temporal location of a handshake. Okay, so our idea in this work is very simple. What we're going to use is something called the conjugate sample of a human action. Conjugate sample is something that contextually similar to the action sample, but it doesn't contain the action. So if you can figure out the differences between the action sample and the conjugate sample, then you can figure out the area or the component that correspond to the action. At the same time, the conjugate sample is contextually similar to the action sample. So the things that so the similarity between them is the context component, right? So if we have if we can collect a conjugate sample, and if we have a method to figure out the differences and the similarities between them, then we can figure out the parts that correspond to the action and the context. So how to obtain the conjugate samples? Well, in this work, we're just going to make the following very simple assumption. Now, suppose that we have an action sample. It is in the middle of a video clip. That's the action sample. What we're going to assume is the video clip that right before or right after the action sample is contextually similar to the action sample, but it doesn't contain the action. So the conjugate sample, so in general, you see that the video clip preceding or succeeding the action sample contain the same background, the same set of people, so we can assume that they share similar context, right? So normally in human action recognition, people that collect a bunch of human action samples, they that clip the video from the beginning of the action sample to the end of the action sample, and they throw away the data before and after the action sample. So what I'm proposing here is not to throw away the data before and after the action sample. So our method here is require the same annotation effort, but it's use more data, but the annotation effort is the same. Okay. Now that we have a way to collect conjugate samples, one question is how to use a conjugate sample effectively. Well, there are several possible approaches for using conjugate sample. The first approach is to subtract the conjugate sample from the action sample. Well, but this approach is, but there's no direct pixel-to-pixel correspondence between the conjugate sample from the action sample, so this approach, wouldn't work very well. The second approach is to use conjugate sample as negative examples, but in this case, this approach ignores the importance of context for recognition. So what we want to do is we want to explicitly separate the action from the context, but we don't want to ignore or to ignore the importance of context for recognition. And the third approach is to use conjugate sample as positive examples, but this corresponding to having noisy labels because the conjugate sample do not contain the action. So having noisy label in the training set would degrade the performance of the classifier a lot. Okay, so what so here's the proposed framework here. Remember that so we have we start with a pair of we have an action sample and a corresponding conjugate sample, which I'm going to denote as A and C. We're going to learn a network for extracting the action component from a video clip, and we call it an F, an action extractor. So if you apply F on the action sample, you get a feature representation for the action component of the action sample, and I call it FA. If it's the same network F, you can apply it to C, and then you get FC. Okay. So these, basically these are the same network, indicating that they share the color indicating that they are the same. Now we want the action component to be different, so because the conjugate sample doesn't contain the action, so we can have a loss function that measure the similarity between the two feature vectors here. So we would penalize for, if we really want FA and FC to be different, and we penalize for their similarity. Okay. At the same time, we're going to train a network for extracting the context component from a video clip. Context extractor G, and if I apply to the action sample A, I have GA, and if I apply it to C, I get this C. In this case, the context is similar, so we want GA and GC to be similar, and we penalize for the differences between GA and GC. Right? So here we have a way to explicitly separate the action from the context, but we want to use both of them for recognition. So we can put both the action component and the context component to a classifier, and then we have a loss to measure the classification loss of this classifier. Okay, so this is the proposed framework for, it's a joint learning framework for the action extractor F, the context extractor G, and the classifier H. So for prediction, we don't need a conjugate sample. In training, we do need conjugate sample, but for testing, we do not need conjugate sample. We just need to fit the action sample to the action extractor and the context extractor, and then fit the feature vector to the classifier to get the classification output. Well, the nice thing about having separate action and context channel is we can, it enables detailed analysis. We can understand the contribution of the action factors by just switching off the branch that correspond to the context component, and we can understand the contribution of context factor by switching off the branch that for the action component. So this is a summary of our approach. We propose a method that automatically separates between the action and the context, and then combine them for action recognition. Our framework enables fine-grained analysis for the action and the context channel, and the framework use conjugate samples. Conjugate samples are easy to collect. We do not need additional annotation. Okay. So let me show you some experiment using this framework. So the first experiment that we perform is on the action trace dataset. So this dataset contains around 3,000 video clips of 13 action classes. And the backbone networks that we use for extracting the feature is a C3D network. It's a C3D network. It's a 3D convolutional network. The input to the network is a block of 16 RGB frames, and the output is a feature vector of 4,096 dimensions. Okay, I should, my illustrating example shows the images, but I should mention here that we work with video, so the input to the network is actually a video, not a single image. Okay. Okay, so this is some experiment result. Now, so here I'm showing you the average precision of for different classes. The average precision, so the higher is the better. And so we have several options here. So either not using the conjugate sample, which is essentially the second column here, and you can choose to use the conjugate sample as either negative or positive examples, or using the proposed framework. So on average, we have the proposed framework has some significant improvement on average compared with methods that do not use a conjugate sample or using them as either positive or negative examples. In many cases, you see a large performance gap for using conjugate sample to training the classifier. Also, using the conjugate sample as either positive or negative example might hurt the performance of the classifier. For example, if you use for recognizing hi-fi, for example, if you're using the video clip before the hi-fi action as negative examples, then the performance of the classifier would decrease like very drastically in this case. Hi-fi in video is very brief action, and the context is very important for recognizing this action. Okay, I think it's all right. Okay, so so we did this work is about like 2 years ago, and at the time C3D network was the state-of-the-art backbone for human action recognition. So that's why we use C3D. We also try to combine it with some other descriptor. Back like 2 years ago, if you want to get to the state-of-the-art performance for human action recognition, you need to combine multiple features or multiple networks. And one particular thing that people prefer to use is to combine a neural network with something called the dense trajectory descriptor, which is something more like using optical flow, tracking the motion of the person and the object, and then build the descriptor around the motion. And so in this case, what we show, so the method that we propose, we call the factor, C3D, which is based on the C3D network, and it's improved the performance than not using the conjugate samples. And even when you combine it with the dense trajectory descriptor, you can still see the improvement for using conjugate samples. More recently, there's better like backbone network, for example, the I3D. So if you use I3D, you don't need to combine it with the dense trajectory descriptor anymore. I3D had 2-channel RGB and the optical flow, and so you see that also in this case, using conjugate sample and the proposed framework also improve the performance of the classifiers. Okay, so now let me show you some video clips that excite the action and the context channel the most. We take a look at the individual classifier, for example, answer phone, and we want to, what I'm showing you as some example of the video clip with high activation, activation score for the answer phone classifier. So on the left, you see those two examples of the video clip with high activation score for answer phone, and so these two video clips are the ones that have the high activation score for the contextual component of answer phone. Okay, so what it's saying is in this situation, these people are more likely to answer the phone. Here are some, some video clips that showing for that excite the action and the context component for several other actions like hug, handshake, and sit up. For example, in this case, they say that these people are likely to hug each other, basically. Also, now that we have a way to separate between the action and the context, we can also try to figure out what are the action classes that are contextually similar to each other. So, for example, we take the classifier get out car, and we ask the question, what are the action categories that are contextually similar to get out car? So, in this plot, what I'm showing is the horizontal bar indicate the differences between the action categories. So, the smaller the bar, the higher the similarity between the action classes. So get out car is, of course, similar to itself. So the next action that is most similar to get out car is drive car. This is not surprising. And the second class that is similar to get out car is run. Maybe in kind of Hollywood movie, it usually show people like driving the car, they get out of the car and they run, start running, or like that. We can do the same for other action category like kiss, for example. Then in this case, a hug is contextually similar to a kiss. We can also analyze the role of context feature now. So being able to separate the action components FA from the context components GA brings some flexibility. We can tune the contribution of the context component for classification. So for example, in this case, if we suppose that we just want to separate between two types of action category, kiss and hug. What this plot shows is if you use the classifier that combine both action and the context, the performance is worse than that if you just use the action component. So for contextually similar action pair, you should not use the context component. You should only focus on the action component. Now, for the contextually dissimilar pairs, like for example between kiss and it, then if you use a context component, it's going to improve the performance of the classifier. Okay. Okay. So this brings me to the end of the first piece of work that I want to talk about, and I'm going to move on and talk about the second, a related work called Attentive Action and Context Factorization. Okay, so what I just show you is in the first part of the talk, we propose a framework to explicitly separate the action and the context, and we train a network for extracting the action component and one network for extracting the context components, and I use different color to indicating the similarity or things that are the same. Supposed to be the same things. Okay, so let me now just try to remove the color so you don't get you don't pay attention, focus on the wrong things here, or you get distracted by the color basically. Okay, so far what I have here, we have an action sample and the conjugate sample, and usually they are represented by kind of three-dimensional array of d-dimensional vectors. So essentially, they are 4D tensor for the temporal, the time, for the height, the width, and then the D is the number of the feature or the channel maps of the network. Okay, and the output of the action extractor and the context extractor are feature vector of k, let's say k-dimensional feature vectors here, for the feature vector, the similarity measure and the different measure can be defined based on the cosine distance of the two vectors. And for example, for the different measure, we use 1 minus the cosine of the two vectors, basically. Okay. Now, one limitation of this approach is it does not support visual grounding. What I mean by that, and even though we can separate the action from the context, we don't know where the action and the context voxel are. And what we want to do in this work is to explicitly, localize the location of the action and the context components in the video. So our idea here is, so instead of building a kind of like a black box action extractor or context extractor, we're going to have a network that, or something called, use something like a mask to indicate the action and the context component of a video. Given the mask, the action or the context mask, we can extract we can identify the action and the context component. So now instead of having a feature vector, we have a three-dimensional array of d-dimensional vector at the output of the extractors too. However, so one technical issue with this approach is we can no longer use the cosine distance to measure the similarity between the two multi-dimensional tensor here, because it's assumed kind of voxel to voxel alignment between, let's say, GA and GC in this case. But in video is dynamic, so the action will, the action and context component will not stay at the same location. So we cannot assume voxel to voxel alignment. So in this work, we propose a method for comparing like 4-dimensional feature maps. So remember that we start with a 3D array of d-dimensional vectors, which is essentially a 4D feature maps. So we look at them as a collection or set of d-dimensional vectors, and let's say hi for m is the number of voxels in the video. Our intuition here is if a component of the voxel is an action feature, then hi is an action feature, then hi should be different from all of zj. Yes, okay. And if hi is an action, okay, sorry, there's a typo here. If hi is a context feature, then hi should be similar to some of zj. So you should be able to find something in the context feature map that's similar to hi. Okay. Based on this intuition, we propose a method to measure the amount of, say, hi in the set z. So we denote it by eta hiz, which is essentially a weighted combination of the component in z, and it's basically by using the softmax function, you take the correlation between hi and the element of the vector in z, and then you take the softmax, and then this is going to be the weight for individual xj. Okay, so zj. So now we can, given the action map S for the spatial temporal location of the action component, we can define the action similarity between two 4D feature map, X and Z. So this is a weighted combination of the similarity between, let me just explain one thing. Okay, so eta hij is the amount of hi in Z, and eta hix is the amount of hi in X, basically. And Si is the action probability for the voxel I. Si, remember that this is defined based on an action map S. And similarity, in this case, we get back to, we can define it based on cosine distance because we are comparing two feature vector now. Similarly, you can define the context differences between two actions, an action sample X and the conjugate sample Z, and is also based on the context map C. So, but this requires to learn to decide which part of the action and the context mask. So in this case, we approximate a binary mask by a probability map. Given a video, we first extracting a 4-dimensional feature map F, and from that we extract the context map C, which is 3-dimensional for the value go from 0 to 1 for the for individual voxel of the spatial temporal location in the video. We're also extracting the attention map for the action, and the action map is the combination of essentially the attention map and what is not considered as the context here, so 1 minus C. Okay, so let me show you some example of what this can, and okay, once you define this, you can plug it in the frameworks that I described in the previous, the first half of the talk. And if you do so, we can now localize part of the video that correspond to the action and the context components. For example, this is the answer phone action, and now we can localize the part that we think that correspond to the action and the part that correspond to the context. Here's another example for KISS. So yeah, here are a couple more examples on the action map for it in this case, and sit down for this. Okay, so yeah, so this is the results on the action thread data set that I showed you earlier. In this case, for whatever which I show it for the two different byte bonds, C3D and I3D, and also the combination with the dense trajectory descriptor. In both cases, the factorization methods using conjugate sample work better than the baseline approach that do not use conjugate samples. Now, if we also try to use the attentive, a mechanism to localize the temporal location of the action component, we can further improve the performance of the classifier. I call it attentive factor I3 method, basically. We also compare with another set of other baseline methods based on different way of pooling feature together, like based on the pose of the person, or like based on the object proposal, or some approach called attentional I3D. Okay. We also perform the performance on some other data set, like Hollywood data set, but I'm probably not going to bore you with all of these dry numbers. All the results are given in the paper. Also, we have results on the HAX 30 data set, which is a newly created or released data set by people at MIT and Facebook, and also result on the UCF 101. If you are interested, you can take a look at our papers. I'm almost done. Okay. Talk summary. Basically, in this talk, I talk about two pieces of work, one on pooling action out of context, and the second one on attentive action and context factorization. Well, if I can, one of the take-home message, it's important to pay attention to the relevant information, and don't throw away data, and use this to guide the attention mechanism of our classifier. If I can have another 30 seconds to shamelessly advertising for recruitment. I'm at Stony Brook University, and we're looking for a postdoc, and always looking for good PhD students. If you are interested, please talk to me. So starting from this year, I'm also getting committed to work at WinAI, which is a newly created artificial intelligence lab at Win Group. We're looking for full-time computer vision researchers. You must already have a PhD to apply. We offer very competitive salary. We're also looking for resident students to basically to commit and work hard for 2 years. We aim to work in research projects and publish papers. The aim is also that you can apply to graduate program in the US after in residency, and then we provide stipend for all the living costs and things. Will be based in Hanoi. And thank you.
Thank you very much. So it's now for Q&A. Okay.
Thank you, Professor Min. I'm John Hurdle, University of Utah. Nice talk. This is not my area, so I'm curious, the kinds of performance you showed with precision. First, is precision, is that always the metric of interest as opposed to, say, recall in these kinds of studies? And are those precisions typical, really, really good? But I can't put those into context.
Right. So yes. So in computer vision and human action recognition, usually we use average precision. So it's the precision at multiple recall. So you plot the precision recall curve, and then you calculate the area under the curve. So to some extent, it's the metric that measures the precision at all the recalls. And another metric for measurement would be to use like accuracy, but in general, it's not. People don't use this as often as average precision. Yeah.
Any other questions? I will have one question. Okay. Going to the first talk. So you have mentioned about annotation. So can you please give more information about the annotation efforts, and so any other idea to reduce the annotation efforts? For example, you use less number of label, conjugate sample, right?
Yeah.
And other unsupervised method for that.
Well, but it's not my idea, but people have come up with many different ways of smartly collect training example for human action recognition. For example, all of the way it's difficult to actually to localize the action correspond to some action of interest. So what people usually do is, or at least some people, including me, would do is we start with what we call the description of the video, what happened in a video. So there's a lot of video where you actually, some fan actually watch a video and describe what happened in the video. Like say, for example, they say, okay, someone sit down with somebody else, or someone like they kiss or something like that. So believe it or not, there's a lot of type of annotation out there describing what happened in the video. The only problem is there's no time information that correlate between that description and the video. So the way we normally done is you use a subtitle which have the time correlation with the video. You use and then you transfer the time from the subtitle with the description, and then you can automatically correlate the description with the video. But that still give you very very noisy annotation. So it still requires some manual verification after that. But regarding how to use this, there's a lot of work in using weakly supervised or noisily annotated example too. So yeah.
I saw in the table there are several kind of action which your method perform so worse than the other. So
yeah.
Could you give any explanation?
Yeah, well, so there's so in this true. So in this data set, there's already 13 actions, but there's in some of the other data sets that we work with, they have a lot of action, like more than 100 actions. So by the laws of large numbers, some the method will work worse in some classes. But typically for our case, it work. It is less effective when the number of example the base classifier is also very weak, so it's very difficult to improve on it too, or it has very higher variance in terms of, or the performance can vary a lot. Yeah.
Yeah. Thank you. Okay, one more question.
Excuse me. Thank you for your presentation. I have a question about the context. So regarding to your presentation, using the context may help to improve the accuracy of action recognition, right? And at the beginning, you also said that we have many types of context. So with the current work, do you, specifically focus on the type, kind of fine-grained context or something like that, or general context?
So in this work, we don't distinguish between different type of contexts. We that assume that it is there somewhere, but we don't have to specify what type of context it is, and we hope that the framework can figure it out, the context, without having to distinguish the type of context.
Okay, thank you. Any other questions? Okay, let's thank speaker.
Thank you.
Okay, so before